We now shift our attention to the first big challenge when using DEM simulations of polydispersed granular materials. This is the simple fact that the particle count can grow significantly in case the size ratio S decreases. Thus, in a polydispersed system, we have simply much more particles for the same particle volume when compared to the coarse particles only case. To illustrate this, I provide an expression for the normalized number of particles NP star in a bidispersed mixture containing particles with a size ratio of S and a plurality of volume fractions delta Q31 of the fines. This simple expression can be found by considering a fixed particle volume and calculating the number of small and large particles in it. The resulting data is visualized in the figure on the right. As you can see, below a certain size ratio of approximately 0.3, there is a steep increase in the particle count when increasing the fines content. Please note that we have used here the number fraction of fines, which is denoted as delta Q01 in this figure. Of course, this normalization with the number of coarse particles is a bit unfair. One can also normalize it with other particle counts, e.g. based on the arithmetic mean or the Sauter mean diameter. I have summarized these results for you in a separate calculation sheet that is available for you on the iMooX platform. When doing DEM simulations, we also have to consider that we need to calculate contact forces for each contact. This is why we now move to the topic of the coordination number that we have already touched in a previous unit. As you can imagine, this number increases with increasing degree of polydispersity for the large particles. As you can see on this figure on the right, this is simply due to a coating effect. The large particle will see a large number of small particles that touch it. Exactly this is a challenge for DEM algorithms, since for each contact we must calculate a contact force. Also, we often have to keep some additional data in memory for each of these contacts, for example, the tangential overlap or the deformation history. We can estimate the number of contacts using the classical model of Suzuki and Oshima for a bidispersed system. Note that a monodispersed packing will have a coordination number that is approximately 6 in case we are near close pack. As you can see, the size fraction determines the number of contacts between small, index 1, and large, index 2 particles. As you can see, the coordination numbers of each particle species, Z1 for the small and Z2 for the large particles, can then be computed from the area fractions of the particle species, here denoted with delta Q21. The plot on the right shows the interesting plot for the coordination number of the large particles, which is denoted as Z2. Note that the coordination number for the smaller particles, Z1, as well as the average coordination number, Z over bar, is lower than in the monodispersed case, and that I have not included a plot for these quantities on this slide. But let us now move on to what really matters. And this is the coordination number or number of contacts on a volumetric basis. Specifically, what I mean is formulated as challenge 2 here. we have more particle-particle contacts per unit volume of particles in a polydispersed packing. For example, we can use the theory of Suzuki and Oshima for a bidispersed system and can come up with an expression for NC star. This quantity is the number of contacts in such a system normalized with that in a monodispersed system, with coarse particles only, that has exactly the same total particle volume. The resulting data is visualized here on the right as a function of the number fraction of small particles delta Q01. As you can see, there is only a moderate effect of the size ratio, but please consider that for small size ratios, the number of small particles is much larger compared to size ratios close to unity. Anyhow, you see the number of contacts skyrockets above a certain number fraction of approximately 0.95, meaning that per unit volume we will have substantially more contacts. Consequently, a significantly higher computational expense for contact detection and force calculation is necessary. To make these calculations transparent for you, I have placed the accompanying calculation sheet, which is called bidispersed coordination number.xlsx, on the iMooX platform. Unfortunately, this is not the last challenge we face when doing DEM simulations of polydispersed systems. And we have to now get even more into the detail, namely into the collision dynamics analysis that is summarized on this slide. As you will understand, challenge number 3 is that the smallest particles dictate the time step of our DEM simulation. The reason is that in order to keep our numerical integration scheme stable, we have to find the critical and in our case smallest Rayleigh time in the system. If we now consider that all particles have an identical stiffness, this yields that the time step size has to decrease with the smallest particle diameter dp min and hence the size ratio. This can be quantified by the Rayleigh time that we have already mentioned in our introduction section. To be precise, the time step has to decrease linearly with the particle diameter, and this is why DEM simulations of polydispersed granular materials are really computationally expensive. We now move on to the last of our 4 challenges associated with polydispersed granular materials, and this challenge is related to multi-phase aspects. Specifically, the 4th challenge is that drag models, as well as other models that are needed to couple the phases, need to be adapted. To understand this in greater detail, let us first have a look at how the drag force is calculated. Consider a single particle in a dense fluid particle flow. Dense means that the particle volume fraction is between 0.1 and the closed packing limit. The drag force Fdi is calculated from the particle volume, a drag coefficient beta Bi, and the difference of the phase velocities. Specifically, this is the average fluid and the individual particle velocity. The drag coefficient is calculated from the dynamic viscosity eta F, the particle size, and the voidage, here denoted as 1 minus phi p. And finally, F. F is a function of the local flow condition, i.e. the particle Reynolds number and the particle volume fraction. And already for a monodispersed system, this expression for F is rather complex. We will now check how f is computed for a polydispersed system. And we see that for such systems, the expression for m becomes significantly more complex. Below, we denote f for a polydispersed system with f di fixed, indicating that the specific expression we will look at will only work for a fixed bed, i.e. non-moving particles. And here it is, the polydispersed drag model of Holloway et al. As you can see, it involves a term that depends on the parameter a, which again depends on the particle volume fraction, and a dimensionless particle size yi. The latter is the particle size normalized with the local Sauter mean diameter. Also, the calculation of the drag coefficient shown here requires data for the monodispersed f value, for which we will provide data in an upcoming unit. Most important, however, is the fact that we need to know the local Sauter mean diameter, or short SMD, which is an additional continuum level information. This indicates that more involved calculations are necessary for polydispersed gas particle flows, explaining why this is considered a challenge in the field of polydispersed DEM simulations.